Sometimes I have an idea for a video that I really want to make, and then I realize it's going to require a lot of context for it to make any sense. Well, that's happening today. Now, the end goal is to explain how we measure redshift. Before we get started with the video, I just want to say thank you so much. We have reached 10,000 subscribers to Nora's Guide to the Galaxy. I appreciate all my galactites. I look forward to telling you way more than you ever wanted to know about the universe. Now, the end goal is to explain how we measure redshift. This is a question I've actually gotten a few times, especially in relation to these new high redshift galaxies being discovered by JWST. And I think it will really illustrate why it's just so amazing that we have observed a galaxy with a confirmed redshift of 14.32. This galaxy, by the way, is called JWST 14 Tech 0, which, like most astronomical names, is very useful but kind of boring and hard to say. So I think I'm going to actually nickname this galaxy Scintilla. This is because it's located in the constellation Fornax, which is Latin for furnace, and Scintilla is Latin for spark. But if we're going to talk about how we measure redshift and why Scintilla is so cool, we probably should have at least a brief discussion of what redshift is and why we even want to measure it in the first place. So let's do that. You can go ahead and skip to the how we measure chapter if you're already familiar with this background. So first, what is redshift? Now, broadly, this is just a general concept that means that the wavelength of the light when it is observed has been stretched out or is longer than when it was emitted due to relative motion between the source and the observer. And if you're thinking, that kind of sounds like the Doppler effect, ding, 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 you get your gold star for the day because that's exactly what it is. This happens with all sorts of waves, including sound waves, which is why one of the most quintessential examples of the Doppler effect is, of course, a siren whooshing by you and that relative motion changing, causing the sound of it to change. Going back to light, redshift specifically refers to the case where the wavelength that's being observed is longer than when it was emitted. And this is because red light has a longer wavelength than blue light, and so we use this concept of an elongated wavelength being redshifted and a shortened wavelength being blue shifted, even when we're talking about light outside of the visible spectrum. If the wavelength is getting stretched out, we know from the Doppler effect that this means that the source and the observer, their relative motion is getting farther apart. To keep things simple, let's just consider us to be the observer as being stationary, observing some object that is moving away from us with some speed, which we'll call the recessional velocity. Then measuring the redshift tells us how fast that recessional velocity is. And note that in astronomy, redshift is usually represented by a unitless number that we call z, and we'll talk more about this later. Okay, so if we measure the redshift of an object, we know how fast it is receding away from us. That's an interesting little bit of data, but why do we care about it so much? Because on cosmological scales, that velocity tells us how far away something is. Measuring distances in space is complicated. We talked before about how you can measure the distance to nearby stars using parallax. And this ends up being the first rung on something that we call the cosmic distance ladder. And cosmological redshift is the final rung on this ladder. Now, all the rungs in between are also very interesting, but we're not going to talk about those today. It's redshift day. And the reason that we can use redshift as a proxy for distance is because of the expansion of the universe. Now, we've talked about the expansion of the universe before, but the TLDW is that the universe is expanding everywhere, all the time. This means that as everything's expanding, everything is getting farther apart from each other. And for any individual observer, the farther away an object is, the faster it will be expanding away from us. This means that an object's recessional velocity is directly related to its distance from us, and we can measure that recessional velocity using redshift. This also explains why we're always talking about redshift, that is, as opposed to blue shift, because since things are expanding, that means they're always moving away from us and being redshifted and not blue shifted. You may be familiar with one way that this velocity-distance relationship manifests, and that is called Hubble's law. This is just a simple linear relationship where an object's distance is directly proportional to its velocity using a constant that we call Hubble's constant. But Hubble's law actually only applies for a certain range of distances from us. For one thing, objects all have their own individual velocities independent of the expansion of the universe. This is called peculiar velocity. And for objects that are really close to us, that peculiar velocity actually dominates over any effect of the expansion of the universe. For example, this is why Andromeda Galaxy is actually blue shifted, because it's really close to us and it's moving towards us due to gravity and its peculiar velocity. But as you get farther away, since the recessional velocity due to expansion is always increasing with distance, eventually it begins to dominate over any object's peculiar velocity. And once we reach this point, that is called being in the Hubble flow. But then, as you get even farther away, things start to get weird. Let's take a little detour into cosmological distances, because it's not as simple as the distances you're probably used to. In fact, there isn't even just one distance. The distance that is probably the most intuitive is just the distance that exists between two objects at a given point in time, and this is called the proper distance. But keep in mind that we only know an object exists because we see light from it, and that light takes time to travel to reach us, and during that time, the universe is still expanding. So we don't actually know the location of us and another object at the same point in time. We know where we are and where the object was when the light was emitted, which is not the same. But we can adjust for that and calculate the position that it would be at the same point in time, and that is the proper distance. Now, because the universe is expanding, the proper distance is always changing over time. It was smaller in the past and it will be larger in the future. Instead, we can think about something called the co-moving distance, which kind of removes that effect of expansion. And so the co-moving distance is actually constant over time. And by definition, we take the co-moving distance to be equal to the proper distance at the current point in time. Now, I mentioned that it takes time for the light emitted from an object to reach us, and this actually gives us another distance, which we call the light travel distance. This is basically exactly what it sounds like. Light travels at a speed, the speed of light, and we have a time. If you take a speed and you multiply it by a time, you get a distance. And the light travel time is the one that's constrained by the age of the universe. So the light travel distance to an object is never going to be more than 13.1 billion light years because the universe hasn't been around for any longer than that for the light to travel. But some of these other distances, they can be more than that. There's also a distance related to how big an object appears to be. An object's angular size is basically how much of your field of view is taking up. And we experience this all the time, right? So as you get farther away from an object in our day-to-day life, that object's angular size gets smaller, even though its physical size, of course, isn't changing. We can do the same thing with celestial objects. If we know an object's physical size and we measure its angular size, we can calculate the distance that relates the two, and this is called the angular diameter distance. Now, unlike in our day-to-day life, the angular size doesn't always decrease with increasing distance. It's weird. A similar concept applies to how bright an object appears to be. As you get farther away from something, it appears dimmer because the energy being emitted by that object is spreading out over a larger and larger surface area. So if we know how much energy an object is emitting and we know how much energy we're measuring it as emitting, again, we can calculate a distance, and that is called the luminosity distance. And for all of these distances, to actually calculate their values in like light years or parsecs, you need to make assumptions about what the universe is like. And so the distance actually varies depending on the cosmological model that you are using. Now, if you look at how we actually mathematically calculate these distances, you'll see that one thing pops up over and over again, and that is z, which is of course the redshift. So if you don't need to know that actual physical distance, why even bother calculating it? Just use the redshift. The higher an object's redshift is, the farther away it is, always. And we can measure the redshift directly, independent of cosmological models, and it's just a simple unitless number, so it's a lot easier to refer to distant objects by their redshift. And this is usually what scientists do, and this is why you'll often hear, the most distant galaxies referred to by the redshift that they're at, and not necessarily how many light years away they are or something. To give you some context on the scale of this redshift value, the most distant thing that we can see, the cosmic microwave background, which was emitted when the universe was just a few 100,000 years old, has a redshift of about 1100. I've already mentioned that the most distant galaxy we've seen, Scintilla, has a redshift of 14.32. Observing this kind of range of redshifts is part of what JWST was literally designed to do. Before JWST, the most distant galaxy had a redshift of about 10. Now, our galaxy group is part of what is called the Virgo supercluster, and the nearest supercluster to the Virgo supercluster is the Hydra supercluster. Now, these are actually both lobes of the larger Laniakea supercluster, but okay. And the Hydra supercluster has a redshift of 0.016. So using a widely accepted cosmological model, this is what the relationship between redshift and distance actually looks like. And as you can see, a little bit of redshift goes a long way. Whew, that was a lot of background. Welcome back to everybody who skipped it. Hopefully we're all on the same page now about what redshift is in the context of astronomy, a measurement of an object's recessional velocity, and why we care about it, because it tells us how far away that object is. But how the hell do we actually measure this thing? And why is JWST so good at it? So measuring redshift goes back to the cause of redshift, which is the Doppler shift. The redshift tells us an object's velocity, and that velocity causes a change in wavelength. So if we can measure the change in wavelength, then we have the redshift. The concept is simple enough, and the equation is very straightforward. It's just that change in wavelength divided by the original wavelength. This is why it's unitless, because you're dividing a wavelength by a wavelength, so you end up with no units. Also, since wavelength and frequency are directly related, you can calculate the redshift from frequencies as well. And it's very similar, it's just the change in frequencies, but the other way around, divided by the observed frequency. But I find wavelength a little bit easier to understand, so that's what we're going to go with, acknowledging that they are entirely equivalent. So it's straightforward, but that doesn't mean it's easy. So to calculate this redshift, there are two wavelengths that you need, the emitted wavelength and the observed wavelength. And there are two primary methods that you can get these two values, the spectroscopic method and the photometric method. Let's start with spectroscopic. To get that emitted wavelength, we turn to good old physics. Astronomical objects can and do emit light over a very broad range of wavelengths, but they also can emit light at very, very specific wavelengths thanks to the quantized nature of atoms and molecules. They exist in certain states that have specific energies associated with them, and so that means the transition between these states is associated with a set change in energy. And for a photon, its energy is directly related to its wavelength. This is a lot easier to understand with an example, so let's go with the most simple example we have, which is a hydrogen atom that's just one proton and one electron. If the electron has its lowest possible energy, that means it has an energy of negative 13.6 electron volts. That's just a unit of energy, don't worry too much about it. If instead it has just a little bit more energy, so it can get up to just the next level of energy, that has minus 3.4 electron volts. So if that electron goes from that higher energy state back down to the lowest one, the energy has to go somewhere and it's emitted in the form of a photon. And because the difference between those energy states is 10.2 electron volts always, that means that photon is always going to be emitted with 10.2 electron volts of energy. And for a photon, if it has 10.2 electron volts of energy, it always has a wavelength of 121.6 nanometers. So if you look at the spectrum, that is the energy per wavelength emitted by an object that has this sort of transition happening, you will see a spike right at 121.6 nanometers. Now this particular emission line from the n=2 to n=1 state of hydrogen is actually called Lyman alpha emission, and you'll hear this come up a lot in astronomy and in this video. That wavelength is the emitted wavelength, so it's one piece of our redshift puzzle. But keep in mind that Lyman alpha is just one of the transitions of hydrogen. It has a lot more, and hydrogen is the simplest atom that there is. So objects are not just emitting one line out there, they're emitting a whole mess of lines, and which ones they're emitting depends on their, chemical composition and energy, and it's not like every galaxy has the same spectrum. Not at all. So yeah, you can take the spectrum of an object and you might have an observed wavelength of an emission line, but how do you know which emission line that is in order to know what the emitted wavelength is that should be used to calculate the redshift? Luckily, we can take advantage again of the quantized nature of these emissions. So Lyman alpha is always emitted at 121.6 nanometers. If instead you have the transition from n=3 to n=1, that photon is always emitted at 102.6 nanometers. That's called Lyman beta if you're curious. So if you just have one emission line in your observed spectrum at say 150 nanometers, that could be Lyman alpha at a redshift of 0.23, but it could be Lyman beta at a redshift of 0.46. There's no way to know. But if you have a second emission line in your spectrum at 126.6 nanometers, then that would be consistent with both Lyman alpha and Lyman beta at a redshift of 0.23. If instead that second line was at 177.8 nanometers, then you would have the Lyman alpha and Lyman beta lines consistent with a redshift of 0.46. So it helps us tell the difference if we look at the spacing between these lines. But again, this is a very, very simplified example that I'm talking about. Here's an example of some real spectroscopic redshifts that are done on some high redshift galaxies from JWST observation. Each color here is a different galaxy. Quick note, this unit here, the little A with a circle on top, is called an angstrom, and it's equal to 10 to the minus 10 meters, or a tenth of a nanometer, and you'll see this come up a lot in spectra. Now these spectra here have had the redshift taken out, so to speak. So this is actually being shown in the rest frame wavelength, that is the wavelength at which it was emitted, not at which it was observed. And that was done by calculating the redshift from the observed wavelengths with all of these emission lines that have been identified. And you can see that the scientists found hydrogen, oxygen, nitrogen, neon, and more, and the spacing between all of these is how they were able to do that and calculate the redshift in the first place. Okay, so we can get the emitted wavelengths using quantum physics and identifying this unique spacing as a fingerprint of different emission lines. But how do we actually measure these observed lines in the first place? I call this the spectroscopic method, so you might guess that it's being done via spectroscopy, and that is true, but probably not very helpful. Spectroscopy is just measuring an object's energy emitted at different wavelengths. Think about sunlight. You normally see sunlight, it's this beautiful whitish yellowish light, but if it hits a prism or a raindrop, it splits out into this rainbow, and you're starting to see the intensity at different wavelengths, and that's why they're different colors. We can do the same thing for light coming from a more distant astronomical object using an instrument called a spectrograph. We won't get into the details of how a spectrograph works today, but the basic concept is that incoming light is split out into different wavelengths with some sort of resolution. That is the smallest change in wavelength that can be differentiated. And a higher resolution means a smaller amount. These spectra that we just looked at were taken using JWST's NIRSPEC instrument. NIRSPEC is the near infrared spectrograph, so it takes spectra in the near infrared range of of wavelengths, which is about 1 to 5 microns. And it has a resolution of 2000 or 25,000 depending on the mode. That's actually not that impressive of a spectral resolution. In my last video, I talked about a high resolution spectrograph that has a resolution of like 190,000. But JWST has some critical features that make it so good at finding these high redshift galaxies, which is how we went from barely being able to find a galaxy at a redshift of 10 to finding multiple at redshifts of 14. For one thing, JWST is pretty big. It has a collecting area of 25 square meters. For comparison, Hubble's is about 4 square meters. All this area helps JWST gather a lot of light, and since these objects are very far away, they're also very faint, so if you get more photons, it's just easier to see them. For another, JWST is an infrared observatory. Hubble is primarily a visible light observatory. Remember, the light from these distant galaxies is being redshifted, so the farther away it is, the redder it is, and some of them are just too red to be seen well in the visible. Consider that Lyman alpha line at 121.6 nanometers. At a redshift of 10, that would have an observed wavelength of 1.3 microns. And that's getting to be pretty close to the limits of what Hubble can detect, but JWST can take these spectra up to 5 microns. And of course, JWST is in space. So that last high resolution spectrograph I talked about is mounted on VLT, and that is a ground-based telescope. Now, infrared light tends to be absorbed by the atmosphere, so it's a lot harder to see these things from the ground than in space. So with JWST, we can take these beautifully detailed infrared spectra that can see these galaxies at much higher redshifts. These spectroscopic redshifts are basically the gold standard. You can measure these emission lines and pin down with really high accuracy exactly what the observed and emitted wavelengths are and measure a really good redshift from that. When an object has a spectroscopic redshift measured, that is considered a confirmed redshift. And this is how we can say things like Scintilla, for example, is really definitely at these very high redshifts. So spectroscopic redshift is so great. Why do we even have another method to measure it? Because taking spectra is hard to do and it's more restrictive. So to make sure that you're seeing light that's just coming from a single object, you have to kind of block it out and do a very focused observation. And you're also splitting the light into these many wavelength buckets. And so you just need more photons to fill all of these different buckets. And so it just takes longer observations. So even though an instrument like NIRSpec can take spectra from multiple objects at the same time, it's still way less than if you're just basically taking a picture of the sky. This sort of taking a picture observation is called photometry, and this gives us the other method of measuring redshift, which is the photometric method. Now, photometry gathers light over a really broad range of wavelengths. It doesn't have a spectrograph that's doing all this splitting into different wavelengths, but there is still some differentiation by wavelength using filters. If spectroscopy is like looking through a prism to see a rainbow, then photometry is kind of like taking a color picture where you're going to have RGB values, but not a full rainbow. Of course, this is just an analogy. That's not exactly what's happening. Different telescopes have different sets of filters, usually with a range of bandwidths. That is how wide the region of the spectra is that they're allowing through the filter. For example, a really widely used photometry system is the Sloan Digital Sky Survey, which has 5 broadband filters called UGRIZ. Hubble has a lot of different instruments with a lot of different filter sets, but for its WFC3 infrared camera, it has 5 wide filters, 4 medium filters, and 6 narrowband filters. JWST's NIRCam has a set of 29 filters. There are 3 extra wide, 8 wide, 12 medium, and 7 narrow. Now, each of these filters basically lets through light at a certain range of wavelengths. So if you have a combined observation from many different filters, you can kind of think about it as a really low resolution spectrum. Definitely, you are not going to be able to be measuring these specific lines using photometry. So you can't use this same fingerprint line spacing method to match emitted to observed. Instead, you need to find some sort of broader feature that you can identify with just a couple measurements at different wavelength ranges. One way that you can do this is called empirical training, or I think nowadays would basically just be considered machine learning. Basically, if you have a really large number of galaxies that all have photometric measurements, and you have some of those galaxies that also have spectroscopic measurements, you can measure the redshift using the spectroscopic method and then see if that correlates with some sort of feature based on the photometric observations and then expand that to your entire data set. You need a lot of data to do this successfully, but luckily there have been more and more large-scale surveys of the universe, so this is definitely becoming more plausible, and some astronomers are having success with this. But since you do need so much data, this is going to be more successful at lower redshifts where you have that kind of data. Otherwise, you have to do a similar thing to what we did with the spectroscopic method and figure out what physics tells us a redshifted photometric measurement would look like and then match that up with your observations. And luckily, physics has our back. The typical spectral feature that's looked for in the photometric method is called a break. And this is basically if you have a place in the spectrum where there's a large change in the overall flux. So it's going to look more like a cliff rather than a spike at a single wavelength. Now, if you go to Wikipedia and you look at the list of the most distant galaxies seen, you'll see over and over again Lyman break galaxy. And indeed, the Lyman break is a very useful feature for identifying redshift in the photometric method. Now, the similarity in name between Lyman alpha emission and the Lyman break is not a coincidence. Any spectral line that is the result of a transition of hydrogen to its lowest energy state is part of what we call the Lyman series. So Lyman alpha is between n equals 2 and n equals 1, Lyman beta is between n equals 3 and n equals 1, Lyman gamma is between n equals 4 and n equals 1, so on and so forth. Now, while emission lines are what you get from the emission of the photon from the higher to lower transition state, you can also have the reverse. So a hydrogen atom that's in its lowest energy state, the electron can get excited by an incoming photon, and this leads to an absorption line. So if you have light coming from somewhere and it hits the hydrogen atom, that particular wavelength will be absorbed. And so this will just show up as a dark line on a bright background rather than a bright line on a dark background. That's an emission line. So these photons that are part of the Lyman series can excite an electron to higher and higher energy states from the lowest energy state. But eventually, photons can get to a high enough energy that instead of putting that electron into a higher energy state, it just strips the electron away from the atom entirely, leaving behind an ion in this case, which is just a proton. And the energy that's required to ionize hydrogen, that is to take that electron away from the proton, is called the Lyman limit. Now, if you look at all of the lines in the Lyman series, you can see it starts over here at that 1216 angstroms, and it goes to lower and lower wavelengths, that is higher and higher energies, getting denser and denser and closer together until finally it reaches 912 angstroms, and then there's nothing after that. And so that 912 angstroms is the Lyman limit. Any photon that has more energy than that can ionize the hydrogen. Now, the way stars form is from collapsing pockets and giant clouds of hydrogen. And so if you have a star forming region, you're going to have a lot of really young, bright stars kind of in the center, surrounded by this neutral hydrogen. So that bright light coming from the young stars, as it passes through this neutral hydrogen, any photons that have high enough energy will ionize the hydrogen, and so they don't pass through the cloud. We don't see the photons at that energy. And so that is any photon that has a wavelength shorter than the Lyman limit at 912 angstroms. But for photons with wavelengths above the Lyman limit, they don't have enough energy to ionize the hydrogen, and so more of them are going to be able to pass through and be observed by us, especially if they have wavelengths longer than Lyman alpha. And this causes a break in the spectrum starting at the Lyman limit up to the Lyman alpha wavelength. And this isn't some kind of squint and you'll miss it type of feature, as you can see very beautifully illustrated here by this very detailed spectrum of Scintilla. And you can see why this sort of feature might be visible even without having a very detailed spectrum. Because of this Lyman break, if you have galaxies and you see them at longer wavelengths, but you don't see them at shorter wavelengths, this is called Lyman dropout, and it helps us identify candidates for high redshift galaxies. And of course, this break is happening at around 1000 angstroms in the emitted wavelengths, but it's getting redshifted with the rest of the spectrum, and so it's being observed at much longer wavelengths. So for example, this would be around 1.8 microns for a redshift of 14. Going back to the photometric filters on JWST, you can see how maybe you would see a galaxy in the 200 filter, but then you don't see it in the 150 filter. And so that could tell you that the Lyman break is happening somewhere in the transition between these two filters. But you can also see why this doesn't give you a very exact measurement of redshift. Let's actually go back, and before we had this beautifully detailed spectrum of Scintilla, we can look at what it looked like with the photometric method. And you can see that this is basically exactly what you see. So the images on the bottom here are showing the photometry of the galaxy, and you can see the dropout that happens between 200 and 150. And this top portion is showing the measured photometry across the wavelength bands, and you can see these red dots from JWST and these light purple ones that are from Hubble data. And in the background, the blue and gold lines are showing two different models of what the spectrum might look like at different redshift. And that blue line is showing the best fit model that they got, so the most likely redshift, and they found that to be 14.5. But interestingly, Scintilla was actually rejected as a high redshift candidate in this paper because of that object that's right to the left of it in the photometry, because it could be contaminating that data. But even though it was rejected as a candidate in this paper, it was still slated to be observed as part of an observational program with the spectrograph. And of course, we did get that beautiful spectrum, and we were able to confirm a redshift measurement of 14.32, which just goes to show how important it is to actually get these spectroscopic observations to confirm high redshifts. And yeah, that's how we measure redshift. We can do a lot very fast with less accuracy by looking for broad changes in brightness in different photometric filters. And we can get really precise measurements from a detailed spectrum taken using a spectrograph, which takes a lot longer and can be done for fewer objects. It's the classic trade-off of quality versus quantity, but both types of measurements are really important in helping us expand our understanding of the early universe. And JWST, with its infrared observation capabilities, is really key in helping us expand our understanding of these really, really distant galaxies. And shout out to Scintilla, aka its real name, the record holder for the most distant galaxy known since July 2024. Love ya, but look forward to your downfall as JWST continues to help us push the limits. Hi, Nora from the future here. So a couple weeks after I recorded this video, another group announced some candidates of very high redshift galaxies out to about redshifts of 18, which would be so cool, but these are only photometric candidates and they have not been spectroscopically confirmed, and so the record still stands with Scintilla as of March 15th, 2025. Thanks for watching. See you again soon. Bye.